So we're in section 2.6, talking about rational functions. So let's start off with talking about what we mean by a rational function, and we're going to talk about how we figure out the domain and how we graph rational functions. So a rational function is we have a function in the form, and we're going to use n for numerator, some function of x over some other function of x, so a numerator and denominator, where n and d n of x and d of x are both polynomials. So we have something like 3x squared plus 5x plus 2 over x squared plus 1. Some kind of the polynomials like we've been working with in chapter 2, we're just making fractions with them, and that's what makes a rational function, as long as we have a polynomial. And our only restriction, we have to be careful, we don't want the denominator equal to 0. We always have to be careful that our denominator is not 0. So our domain, a domain of rational functions, is all numbers where the denominator is not 0. So if you're asked about the domain, you have to figure out where the denominator is 0, and we have to leave those out of our domain. So our domain of a rational function is everywhere the denominator is not 0. So if we want to find our domain, we want to figure out where our denominator is 0, and we leave those points out. So if we're looking at a rational function, f of x is 2x plus 1 over x squared minus 4, and we want the domain. What numbers do we have to leave out of our domain for this function? So x can equal plus or minus 2. So we have to leave plus or minus 2 out of the domain because that makes our denominator 0 and our function is undefined. So our domain would be all real numbers except plus or minus 2, or you could just say x can equal plus or minus 2. Something to say that we can't have plus or minus 2 in our domain. So when the problem asks you for the domain, we just want to figure out, we want to leave out the x values where our denominator is 0. Now with rational functions, where our denominator is 0, if we graph this, what happens where our denominator is 0? What happens to our graph? We get an asymptote, right? Our function's undefined. That means if we divide by 0, we can think of it as infinity. So our function gets really, really, really large. So we have an asymptote. We have several rules for finding asymptotes of rational functions. We can have horizontal and vertical asymptotes. So we have a few rules for finding our asymptotes, and that's a big part of what we're interested in this section. So we want to figure out how to find our asymptotes. And a couple of basic ideas for our asymptotes. Our vertical asymptotes, and I'll give you the rules here in just a second. vertical asymptotes happen where our denominator is 0. Except for there's one exception, and we'll talk about that in just a second. But mainly what we're looking at in this section is we get a vertical asymptote where the denominator is 0. That's where our function's undefined. So that's the way to think of your vertical asymptote. Horizontal asymptote we're interested in what happens to the function eventually. As x gets very large or x gets very small, as we go out in the positive x or go out in the negative x, what happens eventually? What is the end behavior? Our horizontal asymptotes tell us the end behavior. So when we had a straight polynomial, our end behavior was nice. It just depended on the sign of the leading coefficient and whether our power was even or odd, whether it went up and up, down and down, up, down, down, up. So we had some easy rules to figure out the end behavior for our polynomials. When we have a rational function, the horizontal, we get something a little different, and we have some rules to figure this out. But the bottom line is this is what we're looking at. The vertical asymptote is where the denominator is 0. Horizontal asymptotes, we want to figure out what happens to the function eventually. So our rules. And we have three basic rules that we're going to talk about. Our rational function. If f of x, if the, and I'm going to say that the n of x over d of x and d of x equals 0, and n of x is not equal to 0, then we have a vertical asymptote at that x value. So we have to have the denominator equal to 0 and the numerator not equal to 0. If the numerator and denominator are both 0, and we're not going to work with these a lot, if numerator and denominator are both 0, we have a hole in the graph. So if both the numerator and denominator are 0, we have a hole in the graph. Our second rule for horizontal asymptotes. We have our function, and for horizontal asymptotes we need a little more information. We have our numerator, and we have our denominator. And I'm going to write out our functions. Our numerator is going to be a sub n, x to the n, the polynomials that we've been working with. A sub n minus 1, x to the n minus 1, plus dot dot dot, and we go all the way out, plus a sub 1x plus a sub 0. So there's our big long polynomial. And our denominator is, we're going to use b. And we have a big long polynomial here. So this is our rational function. If the degree of the numerator is less than the degree of the denominator, so if we have the degree of the numerator and the degree of the numerator is less than the degree of the denominator, y equals 0 is a horizontal asymptote. So we need to look at the degree of the numerator and degree of the denominator. If the degree of the numerator is less than the degree of the denominator, then y equals 0 is a horizontal asymptote. And that tells us that eventually our graph is going to get close to 0. As x gets very large or x gets very small, our graph is going to get close to 0. Our function is going to get close to 0. Are we good before I move on? We have a couple more rules having to do with the degree of the numerator and denominator.
Could you leave that up first?
Okay. Are you good? All right. Our second rule for horizontal asymptotes: if the degree of the numerator and denominator are the same, if the degree of the numerator and denominator are the same, then the line y equals a sub n over b sub n, which is the ratio of the leading coefficients, is a horizontal asymptote. And so if our degree of the numerator and the degree of the denominator is the same, what you need to remember is the ratio of the leading coefficients. And then one last rule: if the degree of the numerator is greater, we have no horizontal asymptotes. So we have our vertical asymptotes are when our denominator is 0 and our numerator is not equal to 0. Our horizontal asymptotes, we get y equals 0 as a horizontal asymptote if the degree of the numerator is smaller than the degree of the denominator. If the degree of the numerator and the denominator are the same, we get the line a sub n over b sub n, which is the ratio of our leading coefficients, as our horizontal asymptote. If the degree of the numerator is bigger, then we get no horizontal asymptotes. So basically what we're going to be doing in this section is looking at a rational function, figuring out its domain, figuring out where its vertical and horizontal asymptotes are, and then eventually we're going to sketch graphs of these rational functions from our asymptotes and from some function values that we find. Any questions on this so far? Okay. So let's look at some examples. And we're just going to be working today and tomorrow on block day. We're not covering any new material tomorrow. We're just going to practice with working with these rational functions, figuring out our asymptotes, figuring out our intercepts, figuring out our domain, and figuring out what the graphs look like. So let's look at, we'll do a few examples today. Let's look at f of x equals x plus 1 over x squared minus 1. And we want to find vertical and horizontal asymptotes. All right, so let's look at our vertical asymptotes first. Where are we going to have a vertical asymptote? C204. So vertical asymptote, where the denominator is 0. But the numerator does not equal 0. Remember, if they're both 0, we get a whole. And we won't be doing a lot with them. I just want to make sure you understand that you can get them. So if we know that plus or minus 1 makes the denominator 0, what would make the numerator 0 at the same time? Negative 1. So at x equals negative 1, we get a whole, because the numerator and denominator are 0 at the same time. So x equals 1 is a vertical asymptote. How about the horizontal asymptote? And that's going to be the only one. That's the only other value that makes my denominator 0. Josh says y equals 0. The degree of the numerator is larger than the degree of the denominator. So y equals 0 is going to be our horizontal asymptote. Because our degree of the numerator is 1 and the degree of the denominator is 2. So y equals 0 is going to be our horizontal asymptote. So our vertical asymptote is going to be at x equals 1, horizontal at y equals 0. And we have a whole at x equals minus 1. Yes?
Go over that again, like how is the degree to understand?
So the degree of the denominator is larger than the degree of the numerator. Yeah, the degree of the numerator is less than the degree of the denominator. So y equals 0 is our horizontal asymptote. So let's look at another example. 2x plus 5 over 4x minus 6. And we want vertical and horizontal asymptotes. So let's look at our vertical first. So where are we going to have a vertical asymptote? What do we do to find it? What gives us, what happens in our function to give us a vertical asymptote? Denominator 0. And the numerator not equal to 0. So denominator equals 0 when 4x minus 6 equals 0. So I get 4x equals 6, divide by 4, x equals 6 over 4, or 3 halves. So our vertical asymptote, if I plug in x equals 3 halves in the numerator, I'm not going to get 0. So x equals 3 halves is a vertical asymptote. And our horizontal. How do the degree of the numerator and denominator compare? What's the degree of the numerator? What is it? 1. What's the degree of the denominator? 1. They're equal. So the degree of the numerator equals the degree of denominator. So what does that tell us about our horizontal asymptote? How do we find it? It's the ratio of the leading coefficient. So y equals 2 over 4, or 1/2. So y equals 1/2 is our horizontal asymptote. The degrees of the numerator and denominator are the same, so we find our horizontal asymptote by taking the ratio of the leading coefficients. And that's going to be our horizontal asymptote. Questions before we go on? And the last thing we're going to talk about is how we sketch graphs of rational functions. And finding the asymptotes is going to be one of the steps that we use in sketching these graphs. All right, we good? So we're going to have some steps for sketching graphs. We need to find several things. when we're sketching a graph of rational functions, you want to find x-intercepts. The x-intercepts are where the function equals 0. So we set the function equal to 0. And for a rational function, our function is going to be 0, where the numerator is 0. And our x-intercepts are where the graph crosses the x-axis. So when we're sketching a graph, we want to find the x-intercepts. We want to find the y-intercepts. The y-intercepts are where x equals 0. And this is where it crosses the y-axis. So we just plug in x equals 0 and figure out what y is, and that's the y-intercepts are where it crosses the y-axis. So those are going to be our first two steps in sketching these graphs. And we're dealing with polynomials, so we just have a fraction of polynomials, so these are pretty easy. These are usually pretty easy to work with. We want to find the vertical asymptotes. And we just talked about how we find the vertical asymptotes. It's where our function is undefined. Or normally we're looking for where the denominator is 0. So that's where we find our vertical asymptotes. Our horizontal asymptotes, we want to find our horizontal asymptotes. And we just had, we talked about three cases to find our horizontal asymptotes. I'm not going to write them all up here. Our cases have to do with the degree of the numerator and the denominator. And then we want to, once we find all of these things, we want to plot some additional points. So we're going to plot some extra points. You want to plot points between and beyond each vertical asymptote and each x-intercept. So we plot our additional points because our function can do lots of things between the asymptotes and between the intercepts. So you're just picking some extra points, plugging them into your function, and plotting those points on your graph so you get an idea of what the shape looks like. And the places where you want to plot them are between and beyond your vertical asymptotes and your x-intercepts. And you can additionally, you don't always have to do this, it can be helpful, is you can test for symmetry. So these other things are going to give you the most information, but you can also test for symmetry. We'll look at one example, and then we're going to work with this some more tomorrow. So we can look at a couple more examples of graphing these tomorrow. So let's look at an example of plotting one of these functions. So we want to sketch f of x equals x plus 1 over x. So we want to find our intercepts, our asymptotes, and plot some additional points. So our x-intercept Our x-intercepts are where the the numerator is 0. So the x-intercept is where the numerator is 0. So we have x plus 1 equals 0. So our x-intercept is going to be x equals -1, and our y value is going to be at 0. So our x-intercept is at x equals -1. Our y-intercept is where x equals 0. So our y-intercept is where x equals 0. Is there a problem where x equals 0? What is it, Kelsey? What do you say, Josh? The denominator equals 0. So what does that give us? An asymptote. So at x equals 0, we get an asymptote. So we have no y-intercepts. So we get no y-intercept. So our graph is not going to cross the y-axis. Our vertical asymptote we just talked about. We get a vertical asymptote at x equals 0. Now we want to look at our horizontal asymptote. How do the degree of the numerator and denominator compare? They're the same. So what does that tell us about our horizontal asymptote? If the degree of the numerator and denominator are the same, it's the ratio of the leading coefficients. So y equals 1 over 1, or y equals 1, is a horizontal asymptote. So we have a vertical asymptote at x equals 0, a horizontal asymptote at y equals 1. And now we can start to sketch our graph. So let me go up a little bit here, and we'll, here are my axes. And we have I'm going to do my asymptotes in blue. So we have a vertical asymptote at x equals 0. So we have a vertical asymptote here at the y-axis. We have a horizontal asymptote at y equals 1. So we're up here at the line, I'll say that's y equals 1. So there are my asymptotes. Now the reason that we have to plot some additional points is my graph could go here and here. It could go here and here. It could, so we have several different possibilities for where the graph goes. So let's plot some additional points. At x equals -2. F of -2, if I plug -2 in here, I get -2 plus 1 is -1 over -2 is 1/2. So I get over here at -2, I get a point 1/2. And this is y equals 1, so my point is somewhere like this. At f equals -1.5, if I plug that in here, I get that my function is 1/3. So my function's getting smaller here. So that tells me my function here is going to look like so. And then if I plot the point 1, f of 1, so I'm over here, plug in 1, I get 2 over 1. So f of 1 is 2 up here above my asymptote. And I could plug in f of 2. If I put in 2, I get 3 halves. So my function's getting smaller as I go out this way. So my function on this side is going to look like so. If we weren't sure, I could plug in x equals 1/2, and I should get something that's bigger than 2 if you're not sure of the shape. So plot as many additional points as you need to figure out the shape of your graph. And then you just connect your points with a smooth curve. And we'll work more with this tomorrow. All right, homework. Um, 174, we're on page 174, 5 through 11. All right, there you go.